Good morning, everyone. We'll continue today our topic of calculating the electric field due to continuous distribution of charge. We will go through a few steps in order to understand how to set up the integral. So here at the beginning, the first thing we need to identify is the variable of integration. Since we're dealing with continuous charges that are distributed on shapes, those shapes are going to take variables in our coordinates. For example, we've seen in last lecture that the line of charge is basically a one-dimensional shape that has one variable. The variable was along the x. The next step is we need to express my dq, which is the differential charge, this very small charge that I am identifying on this shape that has the continuous charges. I need to express this dq in terms of my variable. Since we're dealing with distributed charges, we have densities, and those densities are related to the shape of that those charges are distributed on. We have seen in last lecture that this shape was a line, where when we calculated the electric field due to the finite line of charge, so the density was lambda, which is basically coulomb per meter. We will see other densities that are related to the area, for example, in this lecture. Then the third step is to express the r vector and also the magnitude of this vector in terms of my variable. Don't forget that r hat in my equation is the r vector divided by its magnitude. Then we need to deal with the direction to see if there's any symmetry in my problem that will simplify calculating the electric field. And then we need to know our integration limit. So those are the 5 steps that you have to be aware of when you set up your integral. Now let's look at those 3 cases where we need to rank in order of increased magnitude of the electric field, knowing that lambda is q over 2a. So the length of my line of charge is 2a, and the total charge is q, and the linear charge density here is q divided by 2a. So we need to rank those cases going from the smallest to the greatest electric field. In order to do this, we can see that the difference between those 3 cases is the denominator. Those equations are already derived for you to use. You can use them right away in case you were asked to calculate the electric field. You only need to know how to operate on this equation. In other words, you should know that the electric field here for this positive charge would be pointing in this direction. So whatever you set up your coordinates, or how the coordinates was set up for you, you should know the direction of the field in terms of the standard unit vectors. But yes, you can go ahead and use the equation right away in case the problems was similar to any of those 2 problems for the line of charge here. Okay, so we need to rank those uh, fields going from the smallest to the greatest. If we look at the denominator here, I can see that the denominator here is d squared minus a squared. Here is d times square root of d squared plus a squared, which is definitely greater than the last one. and then I have these squares. So if I am to rank them from the smallest to the greatest, this one would be, this denominator would be the smallest, which means this is going to give me the greatest electric field. So I'll give this one, I'm ranking them ascending, so this is the greatest electric field. Then comes this one, because I have here d squared is less than d square root of d squared plus a squared, and then this one is the smallest electric field. This one is the smallest. Then comes the point of charge here. Then comes this case. Now let's go to the next case for the ring of charge. So we have seen a line of charge. Now we want to go to the case of the ring of charge. The first thing, as I said, those are the 5 steps. You need to identify the variables in the ring of charge. This is my differential element here. This one is my DL, right? The piece of the ring DL. I need to find what kind of variables that I can relate this DL to. Then I need to express my DQ in terms of this variable. And then I need to express my vector R and my magnitude of this R in terms of the variable. I can see here that the best variable for that ring would be the angle here. If I take this one to be the radius, and this one as my R, I can see that the variable phi here would be the best variable that I can use in this problem. Since it is a circular shape, then I have the radius here as a constant, a, and I can use the phi as the variable that I will be sweeping from 0 to 2 pi. So let's go and derive the electric field for this problem. So if I have my y, x, and z, and this is my ring, then this is y, x. If I take this is to be a, the radius, and this one to be the angle phi, and this piece here is my dl, and then the point that I'm interested to calculate the electric field is right on the z-axis. Let me draw the vector r from this point, and then this would be dE. Now I need to relate my differential element here, which is this little piece that will have the charge on dq. I need to relate it to my variable phi. So how I do this? We all know the circumference of the circle L equals to 2 pi a. 2 pi is for one full circle. In case I have a portion of a circle, then this 2 pi is indeed the amount of the angle here, which is, let's assume that my portion of the circumference is this L, then I can say, so this is, let's assume that this is the C for the circle. Now for this L becomes not the 2 pi, the portion of it, which is basically the phi I have here times A. Now if I derive with respect to the phi, A is constant, I get dl equals to A d phi, right? So this is my dl in terms of the variable. dl equals to A d phi. Now I know that lambda is the total charge, assume that the total charge is q naught or q divided by 2 pi a. What I care about here, that now my dq that is sitting right on this little piece. So dq is sitting on this little dl equals what? Equals the density times this dl, right? Because at the end, this density is Coulomb per meter. My dl here is meter times Coulomb per meter. I get the Coulomb for this little dl. So now I managed to, if I substitute dl with its equivalent, then I managed to create a relationship between my dq and my variable. So dq equals to lambda a d phi. Don't forget that the equation is the general equation k dq over r squared r hat. This is the electric field. So I'm done with the dq. I found dq. Now I need to represent my vector r. This is my vector r. If you look at this vector r, and by the way, this point is h on the z-axis. The height is h. So if I am to write the vector r in terms of the two vectors that I can see here, let me use different colors. So the first vector is going from this dq toward the origin. And this vector has a magnitude of a. However, the direction is minus rho hat. What is this rho hat? This is uh, the radius in the xy plane. So I'm using the rho to avoid using the r because r has been used here. So we can use the rho, which means that this vector now, since it's pointing toward the origin, then that's why it is minus. So this vector is a, magnitude a, minus rho hat. Probably you've used r before, but this time just to avoid using r, we can use the rho hat. So this is that vector. What about the other vector that r is the summation of, is this one. and this one is h k hat, right? H k hat. So my r vector now is a minus rho hat because it's pointing toward the origin plus h k hat. Then my magnitude is square root of a squared plus h squared. So I managed to find all of them. Then I need to decide on the limit of the integration here. I know that the phi is sweeping from 0 to 2 pi. So if I put everything now together, I can say that E equals to integration phi from 0 to 2 pi for k dq is lambda a d phi divided by r squared, which is a squared plus h squared times r hat, which is the r vector, minus rho hat hk hat divided by square root here is half. Now, due to the symmetry, and again, this is very important, if we are to calculate, if we're calculating the electric field right at this point, you will see at every single point on this circle, there is a point on the other side that basically create an electric field such that this electric field is canceling along the row in this circle. So all the electric fields that are in parallel to this circle will be canceled. I only have, as we will see later on here, due to this canceling, I only have a component along the z-axis. So this one will cancel due to the symmetry, and now my integration becomes E equals to phi from 0 to 2 pi k lambda a h d phi k hat divided by, this is will be a squared plus h squared 3 over 2, because this is half and this is 1. If you add them, it's going to give you 3 over 2. So k lambda a h d phi k hat. Now if you integrate, electric field would be, was going to integrating here, all those will go outside and end up with only phi. Then this one is k lambda a h k squared over a squared plus h squared 3 over 2 integration of the phi 0 to 2 pi is going to give me 2 pi, and the final electric field would be 2 pi k lambda a h divided by a squared plus h squared 3 over 2, direction is k hat. Again, you can still use this equation uh, without deriving it if you have a problem with the ring of charge. as shown here. So here we substituted the 2 pi a times lambda with a q, which basically the total charge on one ring of charge. This slide has the summary of what we have done earlier. Now the next step is the disk of charge. We're not going to go into the integration of the disk of charge. You can use it right away. If you want to know how did we come up with this expression, you can contact me and I can go through the detailed derivation of this expression. But I don't want to overwhelm you with deriving this expression for the disk. I just wanted to show you the line of charge and ring of charge, and yeah, that would be it. Here is the disk of charge, basically using the ring of charge and sweeping the radius for ring of charge to give you this expression. Again, this is just for you, for those who are interested to know how did we derive the electric field for the disk of charge using the this approach, which is the DQ approach, uh, or using the ring of charge and sweeping along the radius of this ring of charge. In this case, the DQ would be sigma 2 pi rho d rho, and then you have here the rho in the denominator as well. No, this is not constant anymore. This is not A as we have seen in the ring of charge anymore. This one is changing as well. So it goes into the integration.